We can combine functions by another method. It's called the composition of functions. This method is based on an algebraic process of substitution. So when we are composing functions, we are just doing a substitution. For example, if f and g are two specific functions, and we've defined them this way, f at x is x squared, g at x is the linear function 2x minus 1. Then for any number in the domain of g, let's say x is equal to 3, we can find out what g at 3 is. What would g at 3 be? Well, 2 times 3, 6 minus 1, 5. So if we were looking for g at 3, and just by the way, I don't want you to be confused later, it means that you let your x value equal 3, so 1, g at 3 is 5. We can compute g at 3 and then use the output of that to find the function composed of g at 3. So when we say the function composed of g at 3, then we are just substituting. The function will operate on the input g at 3. So we put 3 into the g function, and we find out what that output is. The output is 5. So we are working this from inside out. What is g at 3? It's 5. So since g at 3 is 5, we substitute 5 for g at 3. Now 5 is going to be inputted into f. So what's f at 5? Well, that would be whatever you put in gets squared 25. That's what we call function composition. So to summarize, you start with the input value of x and calculate g at x. You get your answer to that. You use the answer to that as your input for f, and then you calculate f on this input. That is called f composed of g at x. We use this notation that is an open circle, f composed of g, to denote the function. It's read f composed of g. The domain of f composed of g can get complicated because it consists of the x's in the domain of g, that the output of that is in the domain of f. And so you can get all kinds of restrictions that you may not have thought of. Okay, so first of all, g at x has to be defined, and then what comes out of g at x has to be defined in f. We'll get to that. I'm going to give you a diagram to help you visualize this. So this is like a little machine diagram. So here's the g machine. We put x's in it, and so our input, our x values, go into the machine. So these things that we put into g have to be in the domain of g. So we input x's, and what comes out is the y values, g at x. So our output is the range of g. Then we take the numbers from the range of g, and then we input them. What we're inputting into f is g at x. So the range of g has to be in the domain of f. What's our final output? The things that come out of here have to be in the range of f composed of g. What comes out of here is f. It acted on g at x. Or we might write it this way, f composed of g at x. If x is given to you as a number, like it is here, you're going to get a number for your final answer. If x is given to you as a variable, you're going to get a function for your final answer. So here's your formal definition, and then I will give you a laundry explanation. Formal definition of composite functions f composed of g. The composite function f composed of g of two functions f and g is defined by this. F composed of g at x is f acts on g at x. G at x is the inside function, f that becomes the input into f. For all x in the domain of g, such that g of x is in the domain. Okay, so the laundry works like this. You got a washing machine and you got a dryer. What goes into the washer is called in the domain of the washer, dirty clothes. What comes out of the washer is in the range of the washer, clean, wet clothes. What goes into the dryer is wet, clean clothes. That is, the range of the washer became the domain of the dryer. What comes out of the dryer is clean, dry clothes. F composed of G, the washer composed of the dryer. How do we restrict the domain? So in my family, we have a big laundry basket. And if you put your dirty clothes in the laundry basket, I dump them in the washer. I take them out of the washer and I dump them in the dryer, and I take them out of the dryer and I give them back to you. So if you put something in the laundry basket that can go in the washing machine, like your lovely Angora sweater you just got for Christmas, I'm going to throw it in the wash machine, and that's just fine, but I'm also going to throw it in the dryer, and now it's going to fit the dog. And that's just your fault, because you shouldn't have put it in the laundry basket. You have to restrict the domain of the original if it can't go through both machines. Okay? So let's look at, let's look at an example. So, and I don't have one here, so let's look at this example of how we might have to restrict something. So, if f at x is the square root of x, and g at x is x minus 1, then f composed of g at 0 is not going to be defined. How come? Because if I put 0 into g, what do I get for an answer? -1. And if I put -1 into f, I break the machine. Okay, so even though, so for f, what's the domain of f? X bigger than equal to 0. What's the domain of g? All reals. Domain, all reals. What would be our combined domain for f composed of g? Well, I guess my domain for f composed of g is that x has to be bigger than or equal to 1. Because if I put a number in that's smaller than 1, I end up with a negative going into the square root. So I have to back it all up and restrict the original domain. Okay, let's just do a little bit of practicing functions. So I find this is fun. Can you just fix this typo here? This should say f circle g. F composed of g has domain restrictions of g as well as domain restrictions of the final composite function, like we just saw in our above example. So here's how composition works when you're just using variables. Here's f at x, 1 minus x squared. Here's g at x, 2x plus 3. What is f composed of g? Composition is substitution. It means I have f acting on g at x. I work this problem from the inside out. So composition is substitution. What does f act on? It acts on g at x. What's g at x? Well, let's substitute its definition. It is 2x plus 3. What does f do to its input? Whatever you put into the f function, we take 1 and we subtract that input squared. So what am I putting into f? I'm putting in a 2x plus 3. That is, my f function is going to take 1 and subtract the input squared. What did I put in? 2x plus 3. So this would be f composed of g at x. And of course you would FOIL that all out. Minus 4x squared plus 2 times 3, 6 times 2, plus 12x plus 9. Collect like terms, and I get negative 4x squared minus 12x minus 8. Would you try G composed of F? I'll get you started. Composition is substitution. G acts on the function f at x. So G will act on 1 minus x squared. So 1 minus x squared is what you're going to input into G. Go ahead and do it.